Okay, I wanted to do a quick recap of our congruent triangle shortcuts notes from class today, because I know we're a little tight on time with getting them done, and just kind of maybe for you to hear them again and see them again. What we basically wanted to do was limit ourselves to just knowing three things about two triangles. Okay, as in three pairs of sides and or angles, different combinations, were congruent to each other, and we wanted to see which ones actually resulted incongruent triangles, which will allow us to cut our work in half when we're trying to prove triangles congruent. Because previously, by the definition of congruent triangles, we needed to know all six pairs of sides and angles, so all six pairs of corresponding parts, three pairs of corresponding sides, and three pairs of corresponding angles were congruent between the two triangles. So what we established is that on the valid shortcut side for proving triangles congruent, we have side, 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 three pairs of sides congruent, side, angle, side, two pairs of sides, and the included angle. We've got angle, side, angle. So we've got 1, 2, 3. We've got angle, angle, side. And there's going to be a fifth one that I'm going to add here in a second. Okay, just to point out real quick to take away any confusion, we can call this one side angle angle. Generally, we just do angle angle side, so we're all talking the same language, but I don't want you to get confused. That's the same thing. On the invalid side, when you have combinations that don't necessarily result in congruent triangles, we looked at angle angle angle, and hopefully you recall that that one resulted in similar triangles, same shape but different size. And then we had, of course, our ASS case, which is also SSA if you want to be a little bit more polite about it. Now, one of the things that I think students sometimes get in their mind is just that we can't use it because it's a bad word. That has nothing to do with why it doesn't work. So I'm going to give you a quick visual of why it doesn't work. And we're going to take a look at my setup here. I've got a pair of sides congruent. I'm considering these blue segments congruent. Okay, I pre-measured those. And we've got a pair of angles congruent up here, the green angles congruent. And what I need to do is I need to make a triangle by putting this other side that I have. Okay, so this is my second pair of congruent side because I've got one here and then I've got the same one here. And I need to put that in to make a triangle, but here's the trick. I can't change this angle. So I'm going to go ahead and help myself out here and just give myself sort of an extension here so I can see where that angle goes. And then I'm going to do the same thing over here. And you can see that I'm really pretty close on this side, but maybe I need to turn things. I'm a little shy of hitting on that line. So I'm going to turn it slightly, and maybe about there it seems to be that I'm going exactly to where the angle, and this dotted line means I don't know how long that side is going to be. But I now can say, yes, this angle is congruent to this angle. Of course, the side pair is congruent, and this side is congruent to my other side and my other triangle. Now, here's my question to you. Can you picture on the right-hand side, can you picture me completing the triangle? The side's going to have to attach to here. Can you picture me completing that triangle with that segment, but making a very different looking triangle than the first triangle that you see? And the answer is yes. Okay, of course I could make the same triangle. And it doesn't necessarily mean, when I say it's not a valid method for proving triangles congruent, that doesn't mean that it's not possible to end up with congruent triangles, because I sure can end up with congruent triangles. So if I go with that, pretty close there, that those two triangles are going to be congruent. But it means that there's another triangle that I can make that's not going to end up congruent. Here's what I mean. If I turn this the other way and I slide this in here, okay, I think that's pretty good if I line everything up. Did I use the same side? Sure I did. This side here with my double tick marks is matching up with that one. And I have, between my two triangles, I have a pair of sides congruent, another pair of sides congruent, and a pair of angles congruent. Not included between the two sides, because of course the two sides would meet over here at this angle. So that's why we say our ASS case doesn't work, because right now I have ASS, and I ended up with two very different triangles. Now, to see the exception to this, if I slide this, oh, come on, there we go. If I slide this triangle on top of my first triangle that I made, okay, and try to ignore all my letters that are there, do you see that the two purple lines that I made are sort of split equally between, let's say, an imaginary line that would pass, I hope you can see yellow here, I don't want to make it too hard to see, but a line that would pass right there between them. And my question is, what relationship is that line in the middle, such that my purple lines are kind of the same distance here and here? What relationship is that yellow line to the green line that was the extension of my angle? And if you're thinking along the lines of saying, hey, I've actually got a perpendicular relationship there, that's my special case, because that's the only time when I would not be able to end up with two different triangles that aren't congruent by my angle side case, is when I have perpendicular lines here, which essentially means that I have what kind of a triangle? It's going to be when you end up with the right triangle. And then we have this side is congruent to another side in a triangle, and then the other sides are congruent, and this is what we call the hypotenuse across from the right angle. This is one of the legs. Of course, the other leg is there too, and that could have been the congruent one. This is what I call my HL shortcut, because essentially, when I know that's a right angle, I will only have one possible triangle I can make. It's always going to be the same triangle for right triangles. Okay, that's the best I can do in terms of a visual. If you can't really follow that, it's something you really just need to memorize, but I want you to understand where this comes from, that exception is my fifth valid congruent triangle shortcut, which I call HL. So once again, in summary, okay, just to write it out, HL is hypotenuse and one leg pair are congruent in two right triangles. And if you didn't get a picture from class for that, hey, give yourself a pair of right triangles. There's my pair of right triangles. That's my attempt at a pair of right triangles. I think I can do better than that. There we go. Have to know their right angles. Have to know the hypotenuses are congruent across from right angles, and have to know one of the legs. Okay, so I'm just picking that one. Are congruent, and then I have HL. Okay, but again, just in summary, that is the exception to my angle side case, because if I actually put the letters around there, I have a pair of angles, I have a pair of sides, and I have a pair of sides. And that is certainly not the SAS case. Sides come together down here. That would have to be my included angle. That's not the pair that's marked congruent. So I do have my ASS case because they're right triangles. It works. Okay, I just wanted to help you out for those of you that kind of got shortchanged on the HL shortcut from class. That is my special case of ASS, and the only time that I can guarantee I end up with congruent triangles. So rather than make things confusing and call it ASS, we call it HL since it's specific to working with right triangles. Okay, watch my next video if you want to see how to apply these and see some examples of how I identify which one and distinguish between my shortcuts.